Former dean, current dean, deputy dean, development and research for this opportunity. This enables us, researchers like us, to expose or to showcase our researches to the outside arena, not only within the University of Malaya. And I'm also indebted to my co-researchers and research scholars, without whom I wouldn't have been standing here today. So first of all, I would like to introduce the title, which I christen as From Futile to Functional, Demonstration of Versatility of Local Industrial Byproducts as Building Materials and Products. We all know Malaysia is blessed with natural resources. At the same time, we have abundance of reserve. However, with the growing population, we should work towards sustainable development. Some of the things that I'm going to show you will be eye-opener for some of us. Some of us may know it, but what do we do in the days to come? Look at this, the theory by Elkington in 1988. He was encompassing all the three aspects of a sustainability tool: people, planet, and prosperity. Most of the NGOs fighting for this to get accomplished in their projects. For example, when we focus on the prosperity, sometimes there is a possibility to lose the focus on people and the planet. Therefore, by balancing these three, people, prosperity, and the planet, we can achieve a tool, sustainability tool, that could balance the progress or growth. Also, this slide shows, based on the United States of America's Green Building Council, says that the world population, with 5% of world population in USA, they consume nearly 30% of world's energy, and also 60% of the world's electricity generated, just less than 5% of the world's population. And also the water they use, potable water they use to flush out the toilets every day, it's enough for the entire population to cater for the drinking water. So when we look into the sustainability aspect, we see the certain countries, developed countries, they are in a different arena, whereas the developing and underdeveloping countries have to fight for survival. Also, that's why this body called LEED, Leadership in Energy and Environmental Design, LEED. In America, it's quite popular, and in some of the Western countries, the certification of a building by a third party. In Malaysia, Green Building Index, GBI, is given in Singapore and other countries based on certain criteria that could promote the sustainability aspect. For example, energy is a very important aspect. In most of the buildings, we consume a lot of energy because of the air conditioning, lighting, and other aspects. So it is quite important for us to reduce the energy dependence from the conventional sources. So how do we reduce the energy inside the building, energy usage? So that is given a maximum point in the Green Building Index. Second, water efficiency, also CO2 emission, and improved environmental air quality and stewardship towards the sustaining that kind of aspect. Not only today's construction will be sufficient for this another 10 or 20 years, but we need to cater for another 30, 40, 50, or 100 years, depending on the design of the building. So some of the aspects in Malaysia for Green Building Index, we can see similar to the LEED certification. We have energy efficiency, indoor environmental quality, EQ, sustainable site planning and management, and also material resources, water efficiency, and innovation. The points are listed. So based on this merit, they will give the certification to a particular building, whether this falls under green building category or platinum or silver or etc. This is the requirement. These are the requirement. Look at the cement consumption by different countries. If you look at this one, on the left side, we see the cement consumption by China and other countries. Supposing we compare China with India of equal population, we can see that 57% of cement consumed by China, whereas only a fraction of that by India. So the population growth does not determine only this expansion of the development. It's two contrasting features between China and India. The growth is not stopping, especially on the sustainable. You can look at this. This was an article written by Bill Gates in Washington Post some time back based on the US Geological Survey information. The cement consumption over 100 years by US was only 4.5 gigatons over 100 years period. However, within the 3 years of 2011 to 2013, China consumed more than that quantity of what USA consumed in over 100 years. So look at this next picture. This shows the development of Shanghai in one district, almost within 1987 to 2013, how the vast development of infrastructure changed the whole landscape of this Shanghai district. Today, it's one of the most developed as provinces in China. So, as a researcher, what do we do in Malaysia? We do not want to confine our research inside the university, within the four walls. So our university management, led by our Vice Chancellor, Deputy Vice Chancellor Research, and Dean, Deputy Deans, all are emphasizing on how to move this research forward to demonstrate to the public that these research projects can be implemented and can be useful to the public. That's the reason that we have to demonstrate using the sustainable materials, how we can adapt, how we can implement, how we can use these sustainable materials for the sake of our population, for the betterment of our population. So this project that I'm going to show, 3 or 4 projects, may demonstrate how we have used these materials for the application for the population of Malaysia. For instance, the depletion of natural resources in Malaysia is alarming. It's important that we should preserve the natural materials for our future generation. The second point, the release of CO2 from the building industry is 5 to 7% because of the cement, especially the cement production. Also the rising cost of the building and weaker economy. And millions of houses, not only in Malaysia, but Southeast Asia and Asia in general, because of the population rise, is required. Millions of houses are required. And also there are requirements by various governments on green building index. So this pushes the researchers to move forward and find alternative materials, not the conventional resources, natural resources. So in Malaysia, so as you see here, there are many materials that are displayed here. Bottom ash, fly ash, palm oil clinker ash, palm oil fuel ash, ground granulated blast furnace slag. These powders or ashes or materials can be used as a replacement material. If not the whole replacement for cement, it's impossible in the near future, but maybe in a distant future, far ahead, we can think how to replace the conventional cement using some of these materials. As John F. Kennedy mentioned, the journey of 1,000 miles starts with a single step. So what do we do here? We start with a single step. We want to show that this kind of industrial byproducts, some of these waste materials thrown in the vicinity of the industries could be utilized as a replacement or sustainable materials for the conventional materials. So these powders that you see, they have silica, alumina, and iron oxide. These are the very important characteristics that could be utilized, that can be emphasized to be used as cementitious or pozzolanic materials. So if you look at this, the three cement that you can see that three aspects for each of these materials. It's quite useful for us that we can use some of these materials. Also the scanning electron microscope images show us the nature of these particles. Even though some of these particles are not similar to other, like for instance fly ash, which is widely used because of its spherical particle size and also its pozzolanic and cementitious properties. But other materials, locally available materials such as fly ash, locally available fly ash, ground granulated blast furnace slag, palm oil clinker ash, or palm oil fuel ash, bottom ash, these could be utilized in future based on the properties and also the durability aspect. That's important. And if you look at the availability of other materials other than this, not only the cementitious or pozzolanic, we also have other materials such as slag aggregates from steel industry. Nearly 1 million tons of this slag aggregates produced in Malaysia. And also we have palm oil clinker aggregates, also nearly 1 million tons in Malaysia, with 400 over palm oil mills or factories all around Malaysia. We can use some of these materials which are sometimes thrown in the vicinity of the factories. Also we have quarry dust, which is conventionally used for the road surveys. But it can be centrifuged and to remove the flaky and angular particles. This quarry dust can be used as a sand particle, replacement of passer, sand. So what we do here in Malaysia, there is a factory, they do centrifuge this quarry dust to get it a rounded shaped particles so that it can be used as sand, and it is christened as manufactured sand. Apart from that, we also have other byproducts from the palm industry. That palm oil clinker can be used as powder because this has got cementitious property or infilling property, so that can be utilized. And also these materials, while finding out these quantities or statistics, we can think of how we can move forward by utilizing these materials. And also the aggregates, when it comes to the fine or coarse aggregate, the properties are very important. If you look at the properties, for instance, the palm oil shell that we see here, this palm oil shell is, it's not like conventional aggregate. It's quite different compared to this kind of slag aggregates. We see here the slag aggregate. It has got a rough surface, which are very useful, the rough surfaces, which are very useful for binding or bonding property with the matrix. Also, we have a palm oil clinker aggregates. These aggregates are very porous, very lightweight compared to the slag aggregates, very porous and lightweight. This can be utilized because of the minute pores or bigger pores in this particle. This could be utilized for better bond between the matrix and the aggregates. So the properties are given here, and utilizing some of these materials, we have demonstrated one house constructed within the University of Malaya campus in the Faculty of Engineering. So that's what I'm going to show first as a demonstration project. In this project, we have utilized some of these local industrial byproducts and waste materials. For the replacement of batu, coarse aggregates, we have used palm oil clinker, oil palm shell, and the slag aggregate from the steel industry. And also, as a partial replacement of cement, we have used palm oil clinker ash, we have used fly ash, we have used palm oil fuel ash, and ground granulated blast furnace slag for the pavements. And for the fine aggregates, we have used manufactured sand, which is, as I mentioned, processed from the quarry dust. And as I mentioned, these four binders have been used to replace the cement. And this aggregates the oil palm shell or we have used for the pavements. As I mentioned, slag aggregates and palm oil clinker aggregates have been used in the development of the bricks that are displayed here, the bricks. And we have approached a company to manufacture or produce these bricks for us in the construction process. So IBS was our industrial partner. They enabled us to produce or manufacture these bricks in the factory. So this is the process that you see. And we have used a raft footing as this demonstration model house was being constructed on a car park area. We had to use a raft footing and reinforced U-brick beam and column blocks, brick wall and metal deck roofing. Very simple. It is considered as one-way low-cost model house. So this is the foundation, what you see there, and the construction process. And different phases of construction and the walls and the column being built. And it is 800 square feet demonstration model house. It's built in the vicinity of the Faculty of Engineering. And on the roof, because of the low-cost model, we have used metal deck roofing, as you can see there. And this is the completed house. It's being used for students and researchers, but also we have utilized this for STEM purpose in the past. And the second demonstration project is on the lightweight oil palm shell concrete. Even though this research is quite a little bit older, but still the need for the use of Malaysian industrial byproducts is quite crucial. That's one of the reasons that I'm trying to showcase this second project. How this waste, so-called, today it's not waste, but once it was a waste. 30 years back, this material was not, it was just thrown in the factories. So what you see here is the palm fruit. And after extracting the palm oil, the kernel is also removed or taken out to produce oil. So what you see here is the kernel. But the shell that encompasses the kernel, it's just dumped in the factory. And you can see that the kernel is also used for producing oil. The skin, outside fruit, is being used for palm oil. But what do we do with the shell that's just dumped in the factory? And you can see on the picture at the bottom. So we have collected these shells, and these shells are not like the other coarse aggregates. Hence, we have to investigate the properties, because it has got convex and concave surfaces, as you see there. It's not that easy. It could bond with the matrix, cement or other material. It could bond, but it will not be like the other conventional coarse aggregates. So we have investigated, and we have produced normal weight concrete slabs and the oil palm shell concrete slabs and beams. First, we investigated the beams. That's what I'm going to show. And the properties you can see. The conventional aggregates, 1500 kg per meter cube, the bulk density, whereas this oil palm shell, it's actually less than half, 600 plus. At the same time, if you look at the bottom one, that's aggregate impact value, that was the key factor for us to investigate this further. Because when we hammer the conventional normal weight aggregates, the impact value is quite high, 16.78. Whereas when we hammer this oil palm shell, which is having a lot of fibers inside, it doesn't crumble, but rather it has the energy absorption characteristics. So that's what enabled us to move forward to investigate this shell as as a replacement for the conventional normal weight aggregate concrete. So we have utilized conventional normal weight aggregates in normal weight concrete. We have utilized oil palm shell in this. However, we used additional cementitious material, pozzolanic material, silica fume. I'll tell you the reason later. So the density you can see of the normal weight concrete 2300, whereas for the lightweight oil palm shell concrete it's about 1800. There you can see the difference of almost 20% reduction in the density. It's lightweight concrete, less than 2000 kg per meter cube. Then the workability is quite acceptable, and the compressive strength, Q compressive strength, was almost identical. It's 30, in the range of 30, and we can see the flexural as well as the modulus of elasticity. The modulus of elasticity is a key indicator of its ductile or brittle nature. For instance, this concrete, even though the compressive strength is quite similar, but its modulus of elasticity, Young's modulus, is quite contrasting. One is the normal weight concrete around 26 or 27, whereas for this it's only 12 gigapascal. So I'll explain that aspect later. And this is the graph or the development of the compressive strength that you see here over a period of 90 days. After 28 days, normally the strength development is not high, as we know. Everyone, most of those who are in the civil engineering field would know that. And as I explained before, how do we enhance the bond? Because the shell has convex and concave surfaces. It's not easy for us to get it bonded inside the cement mortar easily. So because of these convex and concave surfaces, what did we do? We have to investigate the surface. For instance, this surface, the convex surface, has numerable pores which are 20 or less than 25 to 30 micrometer in size. Can't see naked eyes. But when we look at the microscope images, we identified this surface has a lot of minute pores, which led us to see how we can improve, because this cannot be bonded with the matrix properly. So this surface is the weakest, one of the weakest surfaces. Unlike this concave surface or the broken surface, this is the broken surface. This broken surface has undulated surface. So these undulations have the ability to absorb or to have some kind of bond. Whereas this convex surface has the weakness in the bond. So what did we do? We tried to use only the plain cement, and we found out that all the pores that you see here on the screen and what you see in my hand, actually the same surface, that 20 micrometer, less than 20 or less than 30, the cement particles, because the size is quite very compared to silica fume, this is bigger, so it cannot filtrate you see that there are voids. Whereas if you look into the next image, when we added the silica fume in with the cement, most of the pores within this, the concave convex surface, already filled with the mortar, or this so-called the binding particles of silica fume, because silica fume is very fine, 100 times finer than the cement particles. So that led us to the next stage of fabricating the beams. What you see is the conventional reinforced concrete beams of 150 by 250 mm size, and we have investigated this with the strain measurements, deformation, deflection measurement, and the load capacity, bending moment capacity. So this is the fabrication of the beam, what you can see there with the strain gauges and with the DMAC gauges. All these were placed, and LVDT was used to measure the vertical deformation. This is the instrumentation that you see. And after the flexural performance test, we found out this is a conventional concrete, normal weight concrete, does not have multiple cracks compared to the oil palm shell concrete. We can see the cracks here, limited numbers. So what happens is because of the limited number of cracks, the cracks widen up, and there is a possibility of brittle failure. Whereas look at this similar beam, same size, same reinforcement ratio, but based on the oil palm shell lightweight concrete. So we can see numerous cracks on the surface compared to the other conventional normal weight concrete. So this led us to understand that this has lot of ductility ability. It has a ductile ability to absorb the load, and you can see the crack weight in the normal weight concrete, it's 0.66 at the ultimate load amount, whereas in the lightweight, because of the number of cracks is more, the width of the crack is less. So that's what we see here. We tested two beams, identical beams, to compare the structural performance. The total number of cracks in the normal weight concrete is only 10, around 10 to 11 number of cracks, whereas in this oil palm shell concrete beam, it was more than 25, around 30 number of cracks. So that shows the more the number of cracks, it shows the bond, it shows the ductility, and the cracks, number of cracks open up, that shows the ductility of the beam. And we can see the development of the crack over the loads and all moment, and also the deflection criteria. As I mentioned, high ductility ratio of about 5 for the oil palm shell concrete beam compared to 2.6 for the normal weight concrete enabled us to understand, oh, this beam or this material has the ductility characteristics. Also, we can use this kind of oil palm shell concrete in the earthquake prone region, because the failure of this type of concrete is not catastrophic. It's not brittle failure. Because of this ductility, the failure mode is ductile. And this is the deformation. We can see that the deflection for the normal weight concrete beam is around 30 to 40 or 40 mm, 50 mm, but for the lightweight concrete, the deflection was about 100 mm. And the strain characteristics also, we compared the strains of both normal weight and lightweight concrete. The strain, because of the bond and because of this deformation, the strain was much higher compared to the normal weight concrete. This led us to the next stage as a pinnacle of our research on this oil palm shell. Where do these findings lead us to? Next stage of our project on investigating whether, because of this ductility, because of the aggregate impact value, can we use this as an impact and blast resistant concrete. So we did it for impact and also the blast resistant concrete. So what you see here is the blast resistant concrete. We have demonstrated, you see the slabs that are being fabricated. The slabs are there, the normal weight concrete as well as the lightweight concrete. And these slabs from the Port Klang have been shipped to Holudo in China through Tianjin Port in China. And we had good collaborators in the form of University of Adelaide in Australia, University of Melbourne in Australia, and Beijing Institute of Technology in Beijing, China. So with these collaborators and researchers from University of Malaya, and we have demonstrated that these oil palm shell concrete slabs are capable of resisting the blast resistant characteristics. We can see here the testing arrangement in a military site in Holudo, China. And because of this sensitivity of these materials involved, because of we are using explosives of 5 kg TNT, 10 kg TNT, so we had to utilize the military experts. The professor from the institute, Beijing Institute of Technology, who is expert in handling the explosives, is setting up the testing arrangement, and the team from this Beijing Institute of Technology enabled us, and also from the University of Adelaide in Australia, they came and helped us. And you can see that the standout distance between the blast panel the oil palm shell or normal weight concrete panel, and the explosive is only 1.5 meter. The standoff distance is quite important. With the explosive or the impact or the pressure waves depend on the standoff distance. So the standoff distance is quite close, 1.5 meters, and you can see the contrasting features of these two slabs. On the left hand side, we see the initiation of the blast through remote. Then the blast is accompanied by fire. There's a pressure and lot of impact on the slab. So there's impact, there's a pressure, and there's a fire. The slabs have to withstand all these three. And you see on the right side, on the top, the normal weight concrete had shattered upon the impact of the blast. After the explosion, after the ignition of the explosives, the slab was shattered, and there are a lot of shrapnels that you can see. The shrapnels are the one that cause damage to the building and injuries to the people, even kill the people because of the shrapnel. So on the other hand, we can see on this oil palm shell concrete, after the blast, we can see these two contrasting features. After the blast, impact, pressure, and the fire, we can see the oil palm shell concrete was intact. I would say that there are numerous cracks on the surface, on this bottom. However, there are no shingle shrapnel compared to this normal weight conventional concrete. Almost equal strength concrete, but because of the energy absorbing, impact absorbing characteristics of oil palm shell, this has happened. This is real for us to show that Malaysian product, which is nothing but oil palm shell, people used to throw this in the vicinity 30 years back. Professor Abang from University of Putra, Malaysia, investigated this oil palm shell. He was the pioneer in Malaysia to investigate this oil palm shell in concrete. Then Professor Manan and our University of Malaya, we have all continued on research using this material. So what we propagate from this research, can we use this as energy absorbing, impact absorbing concrete? Yes, it is possible. We have demonstrated through this project. The next video, short 20-second video, showcase how the blast wave initiated we'll show the short video, 20-second video. It's not sure. This is the two contrasting aggregates with the explosive and technical and impact of fire and oil palm shell. Very important for us to show how the normal weight concrete and the oil palm shell lightweight concrete, how do these beams behave, the materials behave in a different and contrasting features. And what we see here is the simple explanation that oil palm shell concrete is a kind of a method. We can use it as an innovative idea or method to produce lightweight panel or lightweight slabs, and the fibers in the shell enable them to absorb the energy, and it can be useful in impact or blast resistance concrete. And finally, before I close, I would like to also show a simple project that we have also done using some of these materials here. We have utilized in this project the palm oil clinker as a coarse aggregate, and we have utilized manufactured sand as a sand replacement for 100%, and we have used this slag aggregates, and we have also used ground granite blast furnace slag as a cement replacement and fly ash as a cement replacement, and also we have used the we have used the uh, palm oil fuel ash and palm oil clinker powder in this project. This is application of geopolymer concrete. In the geopolymer concrete is nowadays is quite fast developing concrete in all over the world. In Australia, the development of geopolymer concrete is quite huge. In Malaysia, in other countries, there are quite a number of works going on in the application of this. So what do we do here in this? Replace the cement wholly, 100%. We don't want to use ordinary Portland cement. So what do? We need other alternative materials. As I mentioned in the beginning, fly ash is one of the sustainable materials. So far we have been using it, and we have ground granulated blast furnace slag, simply called slag. We do have palm oil fuel ash, we have palm oil flicker ash, we have also bottom ash. So some of these materials, in addition we have metakaolin, we can also utilize. So some of these materials, or in addition there are some other materials coming in the market. These materials, or research market rather, we can utilize some of these materials and showcase to the world that these materials are quite handy and quite useful and durable. So upon the investigation, we found out that these binders can be utilized in the cement replacement. And also the other aspect in geopolymer concrete, why this is not conventionally used, or because of the cost. Because it's not in the market like conventional concrete, and also it's not that easy to get these chemicals sometimes because of the sodium silicate and sodium hydroxide. However, the sodium silicate can be produced using the indigenous materials. So here we are using the conventional commercial silicate and sodium hydroxide. However, there are alternatives available for producing sodium silicate. The aggregates that we show here, the palm oil clinker, palm oil powder, this fuel ash and clinker ash, and the slag aggregates are shown here. They are the alternatives to the conventional aggregates and the materials. So what we see is we have done some kind of, sorry, the previous one, here you see that the structural performance. We have investigated the concrete structural performance, and it's quite achievable. We can even get high strength concrete or medium strength concrete, low strength concrete, depending on the binder content and the mix design. So these are some of the investigations. You can see the shear resistance, the flexural resistance have been investigated, and we have found that this concrete is at par with the conventional concrete. However, how to demonstrate this? So we have used this material to demonstrate and construct another house for this is being used by bus drivers in University of Malaya and also researchers. So this is the outcome of our research. So the pinnacle of all our research should have some kind of outcome. So this is one of the outcomes of the geopolymer concrete, and with that I'd like to also showcase some of the materials that are displayed here. We have a lightweight panel, lightweight materials, foam concrete. We have different kinds of lightweight foamed panels here, oil palm shell concrete. We have oil palm shell concrete. Even though this is having a lot of water absorption, the water absorption is high, we have means to preserve it through different kinds of coating. We can see the blocks that are being displayed here. These blocks are made from the slag aggregate as well as palm oil clinker aggregates. And also we have the panels that are demonstrated here, that the panels are small blocks. These blocks or panels are made of plastic aggregates. We have used the plastic aggregate in the demonstration house of the geopolymer concrete to showcase that the plastics, which are actually not conducive in using in the nowadays in the current world because of the pollution, we can utilize for the some of the civil engineering application. With that, I'd like to take this opportunity to thank again our university management and dean, deputy dean, and the deputy dean development office for arranging this live and demonstration of our research products and research materials to the viewers in different places. So I thank you again. Thank you for watching.